Hello guys, in this video let us look into the continuation of this tectonic study. When we started this tectonic study, I explained about the first theory that was proposed by Alfred Wegener, and we also saw in the course of the lecture we have seen what was the evidences, what was his proposals, and also what exactly were the criticism. The major criticism, when you see in Alfred Wegener's theory, the major criticism which was Alfred Wegener considering it like the oceans to be a passive floor. And he says all the activities with respect to the drift had taken place only on the active surface, that was the continental surface, and he assumed oceans to be passive. Now, based on this, several set of scholars further in the time period came about, and they happened to revive the thoughts of continental drift by saying that not just the continental plates or the continental surfaces, but also the oceanic surfaces have their own activities happening. Now, with this particular brief introduction, I would like to put forward a set of questions. Now, what was that particular event? So this is the major question. What was that revived the continental drift theory's ideology? Now here, for that I have two things to explain. One is Arthur Holmes' contribution, and the second one being Paleomagnetic Studies. But students, to understand these two things, you will have to watch the previous video which we have discussed about interior of the earth. Once you understand that video, these two concepts will be most easiest to understand. Clear? So the question, what actually revived the thoughts of Alfred Wegener or the proposals of Alfred Wegener will be discussed through these two. Now, so let us start with actually what exactly is the Arthur Holmes contribution. Before we start with the Arthur Holmes contribution, look at this image. Before I explain this, let me put forward what exactly is the name he has given to this particular concept. Arthur Holmes called it as convection current theory. So, rather than explaining it directly, I would like to show you a small experiment before I explain. So that experiment video, once you watch it, later on you will understand this very easily. Look at this. See, this is a beaker. It has water in it with potassium permanganate crystals in it. Okay. So now this person is lighting up the flame to this beaker, and look at this. See, what happens in a beaker is what happens in the water is, in the water that is inside, when the water is getting heated up, right? When this water is getting heated up, see, it becomes light. The water molecules will spread as it heats up. It becomes lighter, it rises up. This is rising arm. Once it touches the surface, it meets the surface, the cold mass of water, which is denser than this water which is heated up. Heated up water is lighter. The cold mass tends to sink down. Do you see? So what is happening here is the warm water mass is rising up the cold water mass is falling down. Warm water mass is rising up, cold water mass is falling down. So it is indirectly forming a cycle, right? So now let's get back. This is what I have told you. See here, your flame is there. It's heating up the beaker full of water, and the potassium permanganate which was added there was just to indicate the movement of water, because basically water's color, we cannot identify the molecules moving. So the potassium permanganate helps in identifying the movement of water. So here the warm water rises up, okay, and then here the cold water falls down. So this is the basic convection current theory that you see in water. So the same thing Arthur Holmes said, in our Earth's surface there is a weak zone called asthenosphere. There is a weak surface called asthenosphere. What happens there? Now, before I get into this, you must have a small question. Why am I telling all these things? How is it related to the drift of the continents? Right, I'll explain that part. But before that, how the continents are drifting, to understand that, you have to know what is happening beneath the continents or beneath the surface of the crust, right? For that, we'll have to get a clarity on these things. Now, if you have understood this part, then equate the same thing here. This is the crust. Let me take a different color. This is the crust, right? This is continental crust, this is oceanic crust, this is again continental crust, okay? And this is entirely mantle. What is the spread of mantle? Somewhere from 200 kilometers to 2900 kilometers. These things we have discussed in the interior of the earth video, okay? You can check that video. So in this particular distance, what happens is, it goes, up to 2900 kilometers. Clear? Then comes the outer core and then inner core, okay? So we are worried only about the upper part of the mantle. Why? In the upper part of the mantle, we have a weak sphere called asthenosphere. We have a weak sphere called asthenosphere. In the asthenosphere, what is there? What constitutes asthenosphere? Like when I discussed about the the topics of interior of the earth, I showed you a picture of volcano. Why is that volcano has a molten state of component or molten state of magma that is coming out from a volcano? Why exactly? Who is feeding this magma to the volcano? So these questions can be answered by understanding asthenosphere. What happens in asthenosphere is, asthenosphere contains radioactive minerals. When radioactive minerals are there, right? When radioactive minerals are there, they are the ones which will increase the heat of that particular zone. Okay, so this particular radioactive minerals that is present in the asthenosphere increases the temperature of that zone. That is the reason they are molten in state. Molten state. Is it clear? So what happens is, this molten state of magma, with the increasing temperature as it goes down in the mantle, at the bottom, the more temperature, right? At the bottom it will experience more temperature than at the top. So now let me explain you in a different way. Take the pressure cooker. What happens in a pressure cooker? What happens in pressure cooker? Basically, when it is when it is lit up, right, it develops intense heat inside. When it develops intense heat, it happens to move up and try to find a zone of weak surface so that the pressure is went out, right? So the same way, what happens in this particular scenario is the heat that is at the bottom tends to rise up, here and here, and as it rises up, it finds a weak zone. At that weak zone, it ruptures the crust and it comes out. Okay, so this magma, when it comes out, when it is exposed to this cold water surface on the ocean floor, it tends to become solidified. Okay, how does it get solidified? Look at this picture. It has got solidified into a mountain, right? These mountains, we call it as ridges. These mountains, we call it as ridges. Now, let me show you one small picture. Look at this. This is an image which shows the distribution of volcanism and earthquakes on the surface of the earth. Now, can you see these dots here? Can you see these dots here? Now I have a question for you. Everywhere, why are these particular dots in a straight line? And why exactly at the mid of the ocean? Right? So for these questions, we will find out an answer very soon. See, this is what the ridges I told you. Like this, the series of ridges are formed. Why? This is the part where the magma erupts out. When the magma erupts out, it gets solidified on the surface and tends to become like ridges. Okay, so this is what I was telling you. At the rising arm of the convection current, this magma erupts out to form ridges. When they form the ridges, right, not entire magma comes out, right, but the other part of magma just gets cools down and it falls down. So this circulation of magma within the asthenosphere was the concept that was propounded by Arthur Holmes, and it was called as the convection current theory. Is this clear? So what he propounded here was the same concept that we have seen with respect to the water and potassium permanganate experiment. Is this part clear? So the convection current theory is one important thing that you will have to understand for now. So now, if you have understood this part, then I have a small question. Like, this was Arthur Holmes' convection current theory, which we have understood. Now, what is paleomagnetic studies? But before understanding what is paleomagnetic studies, answer this question. If the ridges are forming at the weak zones, right? The magma is coming out and the ridges are forming. But then if the ridges are forming frequently, then it has to build up and come above the surface of the water. Why is it not happening? That's my question. Think about it, guys. Am I right? I should be right here. If this particular magma is coming out frequently, right, then this magma is building up the ridge. When it is building up the ridge, with the accumulation of more magma, with the it should increase in size. The increase in size should even exceed the sea level. Why did this not happen? We don't see any mountains erupting. We don't see any mountains that has come out in a long chain of mountains like that of Himalayas or something that has come out of the surface of the water, right? from the base crossing the surface of the water and appearing, right? Then what happened to these ridges? This is my question. So here, before we understand that, let me tell you one more concept. I'll explain this concept, but keep this in mind. I'll explain this concept. What happened to these huge ridges that is been forming since ages? The second thing is, now, before I start with paleomagnetic, what is paleomagnetic studies? See, Earth has magnetic poles. See, so here, this is north, this is south, right? So our Earth's magnetic poles are inclined in such a way, the magnetic north is towards the south, and the magnetic south is towards the north. Here, will this particular in a direction of magnetic north and south be always constant like this? No. Earth has a property where every few million years this magnetic north and south are reversed. Okay, so let us not go much detail into this. Neither our NCERT asks us to understand so deep. So just understand for now, the geographical south houses magnetic north, geographical north houses magnetic south. Right. How do I know this? That is where I'll explain you this paleomagnetic studies. Paleomagnetic studies is understanding the magnetic inclination or magnetic properties. Understanding the magnetic properties that is housed in rocks or any sort of other old equipments or minerals or something like that. Floor, ocean floor, all these things. Clear? So basically it is from the rocks they tend to get to know. Now let us understand how this paleomagnetic studies, what is this paleomagnetic study and how it helps in reviving the continental drift theory, right? So now this part you must have understood, right? So what happens here is, whenever this magma comes out, the rising arms whenever they meet, it comes out to form ridges. Okay, so whenever they come out and cool down and solidify, right, this particular, the solidified magma, right, what is its nature? It is basically a basaltic magma. What do you mean by basaltic? Basaltic is basically based on the composition. This will be very less in silica and very rich in iron. So when it is rich in iron, can I say when it is rich in iron, it is having more magnetic property, right? When suppose let us say now the magnetic north is here, magnetic south is here. Okay, this basalt has solidified. So doesn't the minerals that is there in this solidified ridge, right, incline or align in this direction, right? When this is north, it will be south. When this is south, it will be north. Correct? So what happens is, After few million years again, when the same phenomenon recur, when they recur, what happens is, suppose the geographical north and south remain same, but the magnetic north and south changes. Suppose the geographical north has magnetic north and the geographical south has magnetic south. Earlier, this was magnetic north, this was magnetic south. So that's why we have this. This time it changes. So what is happening in this particular phenomenon is, every time the magma erupts out of the surface, from the surface, and gets solidified, it gets inclined to the existing magnetic north and south. Is that clear? So based on that, what happens is, look at this. The first time it has erupted, what has happened now? Let us not take this as the recent one, right? Why is this recent one? This is recent one because the magma chamber is here. The recent magma eruption and solidification. So I'll call it as A. Before this, these has happened, the ones in the orange, I'll call them B. And before it, this has happened, I'll call it C. Now what has happened here is, I can differentiate the different polarities among these three sets of ridges, right? How is that possible? See, suppose when this was erupted, right? When this was C was erupted, the magnetic inclination, let us say this is geographical south, geographical north. When this C was erupted, the geographical south was towards, magnetic north, magnetic south. Okay, so the inclination is like that. Let me call it as Z1 band. Let us take B. During B, now the polarity or the magnetic poles has changed. So now it is magnetic south in geographic south and magnetic north in geographic north. So I'll call it as Z2. Again, let us take A. Now present situation. In geographic south, we have magnetic north. In geographic north, we have magnetic south. So it is same as this one. So I'll call it Z1 again. So what is happening is, this is Z1, this is Z1, this is Z1, this is Z2, this is Z2. So you see that bands are reversing. When these bands are reversing, that shows there is frequent change in the magnetic poles, right? So here what is happening is, basically the magma, whenever it gets erupted, it just happens to solidify and then form these bands, reverse bands of magnetic polarity. Is this clear? So this, when they studied with this concept, when the geographers studied, they came to a question that if ocean floors were passive, then how can these rocks be so young? How can these rocks show diversity? So this was the question. Okay, so when this was the question, that revived the concept that was proposed by continental drift theory. Okay, so now you understood what is paleomagnetism and you have understood what is the contribution of Arthur Holmes. So with these two basic understanding, we can study what is seafloor spreading. Seafloor spreading. See here, what I would like to explain here is, I have a question. Which one is the youngest? The oceanic crust or the continental crust? So for that, And also I asked you one more question. Every time the magma erupts out, it cools down and solidifies to form a ridge. So every time the next episodes happen, it must accumulate and grow up in its physical height to that extent that it can even cross over the surface water, right? Sea level surface water. So these two questions I'll answer through this particular seafloor spreading. To understand seafloor spreading, one need to understand convection current theory and also the paleomagnetic studies. So that's why I happen to give a basic of it, and then now we will understand it in a better way. There is this convection current that is happening in the asthenosphere. This is asthenosphere. This is asthenosphere. So here the rising limb of magma, when they meet at the weakest zone, they come out, cool down and solidify to form the ridge. Right. But I told you not the entire magma is coming out. Correct. So the other part of magma that is moving like this, right? The other part of magma that is moving like this, right, is actually sliding apart this plates. So these plates tend to move in opposite direction. When these plates move, right, why are these plates moving? These plates are moving because of the convection current inside. Is this clear now? When these plates move, the old solidified ridge also moves. Next set of magma that comes down cools and forms a ridge. Again, when this second set moves, third. So second set is here, the first one is here, and now the third one is here. So what is happening, every time it comes onto the surface, gets solidified to form a ridge, it gets inclined. It's the rock when it is getting to form rock, or when it is getting solidified, the magnetic magnetic property, the magnetic things that is there in the magma inclines itself to the existing magnetic poles. This is paleomagnetic that we have studied, and this is how the banding happens. Okay, and because of this convection current, the plates are drifting or the seafloor is spreading. Now the next immediate question you should get is, if this is spreading, what happens to that particular part which is at the corners near the continents, right? What happens to these plates near the continents is that what happens is suppose this is the continent. This plate is moving like this. This plate is moving like this. When they both converge, this being heavier, why is this oceanic plate heavier? Because in the previous lecture I have told you this is made up of Sial, silicon and aluminium. This is made up of Sima, silicon and magnesium. So this is heavier than this. So when they converge, the heavier one will fall down. When the heavier one falls down, right, what it forms is a trench. So what happens here is, we have heard, like in the first class when I was telling you continental drift theory, I asked you a question, why do we have several variations on the surface of the crust? Then I asked you the deepest point which we have heard so far is Mariana Trench. How is that formed? Right? Here is the answer. When the convection current theory pushes the plate, right? When it pushes the plate, what happens is it gets resisted by the continental plate, and since the heavier plate is here, it just sinks down and melts to add magma to the magma chamber, and here at the junction it forms a trench. Okay, so this is the basic understanding of seafloor spreading theory. Now, if this is like seafloor spreading theory, yes, fine. But how do I believe it? What are the evidences to prove that seafloor spreading theory is happening? Yes, that's a good point that we have to discuss. What are the points that I can believe that makes me believe that seafloor spreading theory is happening? There are two things. One, geographers have studied the age of the ocean bottom surface. The age of the ocean bottom surface, when studied by geographers, they found that the youngest formations of the oceanic crust are near the ridges. Can you see this? Youngest are near the ridges. And as they move away from the ridge towards the continental surface, what they see is the age of the rocks increases. Why is it so? Because the seafloor spreads, the magma comes out, forms the new crust. When it is spreading at this junction, the old one is just getting interacted in a convergent relationship with the continental plate, and then it is sinking in to destroy the old mass. Right? So this is how the old mass of oceanic crust is frequently demolished and destructed, the new mass is being constructed. Now there is one more question. Is this the mechanism happening only to the oceanic crust, or does it happen with the continental crust? Yes, let us discuss that in the plate tectonics theory. Okay, so but this is the mechanism, and this evidence of finding the youngest oceanic crust near the ridge and oldest at the margins is the first evidence to prove seafloor spreading theory. And the second one was this particular thing. Almost this picture shows the volcanic and earthquake distributions across the world. Most of the volcanic ridges are found at the mid of the oceans. This is Atlantic mid-oceanic ridges. This is Pacific, and this is Indian Ocean. So you can see that these areas, the volcanism happens, that shows the ridges are formed due to volcanism, and the volcanism happens because there are types of volcanism, but this is not that volcanism that blasts off as you see in the movie 2012 or any other movies, right? So this is a very silent volcano. It just happens to split like this. See, if these are the two plates, they just move apart, okay, and when they move apart, the magma comes out and forms the ridge. Okay, yes. What happens when the ridge is formed? When they are getting solidified, it has to lose the heat. Generally, it is believed for every 300 meters, around 9.4 degrees Celsius of temperature will be the change in the ocean water. But what happens is, at the zone of these ridges, what the geographers or oceanographers have observed is that the increase in temperature is more. Okay, or the change in temperature of water is more in this region. That is because of the presence of these volcanic activities. Okay, so these are the two important evidences to show that the seafloor spreading is happening. Okay, so let us take up the next part, tectonics, plate tectonics, in the next video. Thank you.